back at the start of the class, I had calculus equals pre-calculus, which was your algebra and trig, plus the concept of limit. And so we spent like a week or so on limits, and we took, if we took limit and we added it with slope, that gave us the derivative. So next week we're going to formally start the study of the other half of calculus called the integral calculus. Okay, limit plus sums is going to give us integrals. And it turns out, spoiler alert, that derivatives and integrals end up being more or less inverse operations. So the last section here in chapter 4, the last application of derivatives, is antiderivatives, and that's when we start turning this around. So basically, here's what we're doing. What we've been doing up to this point in chapters 3 and 4 is, okay, f of x is x squared plus 5, and then I would ask you, what's f prime of x, and you would all tell me what? 2x. So basically, antiderivative is f prime of x is 2x. Question, what's f of x? And, well, one answer is what? X squared plus 5, but there's other answers too, right? I could just do straight up what? I could just, we could just do x squared, you follow? Or I could do x squared plus, or x squared minus 1. You with me or not? So antiderivatives, going backwards, is essentially what we're doing. So there's a definition. The tradition is, if you have a function little f, capital F is going to represent the antiderivative. Capital F is an antiderivative of a function little f on an interval I. Typically we look at antiderivatives on intervals. If capital F prime of x is lowercase f of x. So for example here, verify that capital F prime is an antiderivative of little f. So basically, to show this is an antiderivative, you need to calculate the derivative, and you need to show capital F prime of x is little f of x. Now I'm not going to go through this because it's all spelled out here step by step, but the point of having this here at the beginning is just to remind you of the rules we have of derivatives, okay? Because all these rules that are going to carry over, well, most of them will carry over to antiderivatives. So you just start taking the derivative. Remember the rules for derivative. You plug a value into your function, and the last operations are the first derivative rules you apply, right? So the last operations to simplify capital F of x would be the addition. So the first rule we apply is going to be the sum and difference rule. Then we can factor out the constants, and then we can go on our way, okay? So those kind of strategies that you've been using, hopefully now, sort of just without even thinking about it, because you've taken so many derivatives now, are going to come to play when you go to calculate antiderivatives. And sure enough, if you go through and simplify, you find that capital F prime of x is equal to little f of x, which shows it's an antiderivative. Now we mentioned this. You know, if you're trying to solve f prime of x equals 2x, you could get x squared, and then you could have any constant tacked onto that, and that would still work, right? Because you take the derivative here, when you add the derivative of that constant, it's just going to be 0. But then you could say, okay, well, are those the only antiderivatives? In other words, is that how you catch them all? You just tack on a plus c? And the answer is yes, because of the mean value theorem. So that's this theorem here. Antiderivatives differ by at most a constant. More specifically, if little f is continuous on an interval I, and capital F and G are antiderivatives of f, then there is a constant c so that f of x equals g of x plus c. Right? So what this does is, for example, let's say the derivative of x is cosine x. What this enables us to do is say, okay, can you think of a function whose derivative is cosine? Yeah, who? Sine of x. And if you want to capture all of them, right? If you want to catch all the antiderivatives, all you have to do is tack on a what? C. And you're guaranteed that every antiderivative is going to be one of these. You follow? Now the proof of that, it's kind of like a two-liner because it has to do with the mean value theorem. So suppose capital F and capital G are antiderivatives. For a function little f on some interval I, then that means that capital F prime, the derivative of big F is little f, and the derivative of big G is little f. So consider capital H, which is capital F minus capital G. Then what would capital H prime be? Well, that would be the derivative F prime minus the derivative G prime. But what's capital F prime and what's capital G prime? They're both what? Capital F prime is? Capital G prime is? So H prime is what? 0. And what do we know, courtesy of the mean value theorem? If you have a derivative that's always 0, that means that that function is always a what? Constant. You follow? So that means capital H is a constant, which means that F minus G is a constant. And so there we have it. Make sense or not, folks? Okay? So basically what this means is that if you're trying to find antiderivatives, you just have to find one, and then you capture all of them by tacking on that plus c. And hopefully that makes sense. Geometrically, let's talk about what that plus c really does. Think back to algebra on this. So let's take your f of x, we'll call it little f of x cosine x, and then capital big F of x is sine x plus c. Remember, back to pre-calculus or college algebra, when you add on a c to a function, you're just adding the same constant to each of the y values. So when you move the c around, all you're doing to that function is moving it up or down. You follow? Does the derivative care where you are up or down? The derivative is just talking about the what? The slopes. So the slopes of all these blue curves are going to be the same. You follow? So they all have the same derivative. So here's notation. This notation will not make a lot of sense until next week. But here's the notation. We have this. This is sort of an elongated S. This is called the integral sign. Now when you integrate something, you gather something together, right? You sort of put everything together. So we'll talk about why, what's going on there. F of x is the function, and then you got your dx, that's your differential in x. That's kind of what we talked about yesterday. Basically what this is saying is this is asking you for the family of antiderivatives of little f. All right? And so knowing what we know from the mean value theorem, your answers to this are always going to look like some function of x, f of x, plus your c. All right? So on your test, over the weekend on your test, there's 5 antiderivatives you have to do. The first thing you want to do is, when you get to that problem, put a little plus c up at the top so you remind yourself to put the plus c on. Okay? Now, there are 2 kinds of instructors. Like if you forget the plus c, some instructors will take off a point for every single antiderivative, which is silly because it's the same mistake like 17 times. But I will take off at least a point. And we'll see here when we get into one of the applications how important it is to have that c, because there's a lot of information that can be contained in there. So for example, if I want the integral cosine of x dx, this is saying I want all functions whose derivative is cosine. And we know a function whose derivative is cosine, which is sine. And to get all of them, we're going to tack on a c. And the best way to check is to take the derivative. And I highly encourage you to do this. Now, once again, you can take derivatives using Desmos and checking them that way as well. All right, I encourage you to do that as well. But especially because we're over the summer term, this is a great way to review the derivatives. The more you practice derivatives, the better you're going to get in antiderivatives. Does that make sense? Sure enough, what's the derivative of sine? What's the derivative of plus c? And so there you go. The function you're integrating is called the integrand. All right, so if you hear me talk about the integrand, doing stuff to the integrand, it's the function you're integrating. This, the x here, tells you this is the variable of integration. So just like when you took the derivative dx, sine of x, or dt, t squared, or dy, tangent of y, okay? This was the variable of differentiation. You were taking the derivative with respect to x, t, or y. This tells you the variable of integration. And once again, this notation will make sense after what we do next week. Just for now, that's just what it means. All right? All right, let's take a look at this example. We know that the derivative, let's see, what's the derivative of sine of 2x? So what happens if you have that constant multiple in there? You're going to get your cosine of 2x, but then what's going to pop out? A 2, right, from the chain rule. You follow? So if I wanted the integral of cosine of 2x, I would need a function whose derivative is cosine of 2x. Well, I almost have it here, you follow? Except I'm off by a factor of what? 2, which is a constant. You follow? So it's not going to quite be sine of 2x, because when I take the derivative of sine of 2x, I multiply by a constant of 2. So to counteract that in the derivative, I'd have to do what? Make sense or not, folks? Okay. Now, caution. This kind of thing works well with constants. Okay, so these are a constant. The derivative of, say, sine of x squared is what? That would be 2x. Cosine of x squared is the integral of cosine of x squared 1 over 2x sine of x squared. Well, here's the difference. Constants factor out when you take derivatives, right? Do variables factor out? No. So if you've got variables in there, we're going to have to try to do something else to fix the variables. You follow? If you take the derivative of this, you'd have to use either the quotient rule or the product rule. and you're not just going to get that. So this works well for constants, and we'll see that in our formulas. All right, properties of the antiderivative. Once again, all of these properties are inherited from the properties of derivatives. So if you've spent time taking countless derivatives here throughout the homework, then a lot of these are going to seem like second nature to you. Constant multiple rule. You can factor constants out of derivatives, so guess what? You can factor constants out of antiderivatives. Make sense or not? The check would be to take the derivative of this, the derivative of the constant is 0, k factors out. The derivative behaves well under sum and difference, so does the antiderivative. All right, let's talk about some basic formulas. What's the derivative of x? 1. So the integral dx, which really means 1 dx, is going to be what? X plus, of course, a c. Let's talk about the power rule. I used p there. Okay. So let's talk about the power rule. I want to take the derivative of x to some power. It's a two-step process, right? The first step is what happens to the power itself. You multiply by the power, and then what happens to it? It gets demoted, right? You subtract 1. So that's a two-step process. Multiply by the power, and then subtract 1 from the power. All right? That's like a two-step process, like putting on your socks and then putting on your shoes. If you want to reverse that process, unless you're very talented, you take off your shoes and then you take off your what? So if I want to reverse the process, I would first reverse subtracting 1. And what's the opposite of subtracting 1? Adding 1 to the power. So that'd be the first thing I do. And then instead of multiplying by the power, I would do what? Divide by the power. Make sense or not, folks? And this formula works perfectly well, provided what? I can't divide by 0, so p can't be -1. So at this stage in the game, folks, we don't know what this integral is yet. You follow? We will by the end of the course, which isn't just, so you only have to wait like a couple weeks. Okay. But yeah, so for example, if I want the integral of x cubed dx, I'm looking for all functions whose derivative is x cubed. So the power rule says, okay, I got to reverse the power rule. So instead of subtracting 1 from the exponent, I got to do what? Add 1. So the cube, the 3, becomes a 4. And instead of multiplying the power, I do what? Divide by the power. You follow or not, folks? And what's the ultimate check? Take the derivative. The plus c, that's going to go to 0. That 4 is a what? Constant. So I can factor it out. That's going to come out as a what? Since it's in the denominator, it's going to be a 1/4. What's the derivative of x to the 4th? 4x cubed. By golly, I get x cubed. Make sense or not, folks? We know the derivative of sine is cosine, so the integral of cosine is sine plus c. The derivative of secant is secant tangent, so the integral of secant tangent is secant plus c. The derivative of tangent is secant squared. You follow or not, folks? And once again, here are the cofunctions. What happens with all the cofunctions? We attach that negative. You follow? Because when we take the derivative of all those cofunctions, what pops out? A negative. You see what's happening or not, folks? Other common formulas. So this is like the sine of 2x thing. All right. So if you take the derivative of a cosine of kx, a factor of k is going to pop out. So you take care of that constant by that. So k, these are constants. So for example, the integral of secant of theta, tangent of theta, d theta. Well, what function has a derivative secant of theta, tangent of theta? Answer, secant of theta. To capture all the antiderivatives, I tack on a what? Plus c. Okay. You ever see those Flex Seal commercials? It's like kind of like a meme. They just slap on the Flex Seal. That's all. We're just slapping the c on. It's like, you know, you can imagine it's a factory. We're making antiderivatives. The last thing that happens before it goes out the door, you just slap on the plus c. So if I want to integrate secant of, Jacob, what's your favorite number? 5. 5 theta, tangent of 5 theta, d theta. Once again, this is a constant. We know that constants can easily factor out of derivatives. So this is going to be not secant of 5 theta, but what? If you took the derivative of secant of 5 theta, you have secant of 5 theta, tangent of 5 theta times 5. So you'd have a 1/5 out front. Make sense or not, folks? And I can't stress this enough. The best way to check your answers is by taking the derivative. Take the derivative and see that it matches the integrand. All right. If it gets a little messy, take the derivative on Desmos. Be forewarned that just like with derivatives, the back of the book will sometimes do all kinds of crazy machinations. We were lamenting about this in Calc 2 yesterday. One of my students stays behind every day in Calc 2 to work on things. And some of the homework just gets ridiculous. You look in the back of the book, it looks nothing like, you know, what they had, but what he had is correct. You follow? So check your answer by taking the derivative. If that gets too messy, use Desmos to check, because there's a good chance that you're correct, that there's just been some shenanigans. All right, so once again, if you have flashcards with the derivative properties on it, you know, flip them over and put the integral property on the back of it. You follow? And just practice them every day. All right, let's do some examples. We're going to find the following antiderivatives. Check your answer by taking the derivative. So we got integral 3x minus cosine 2x plus cosecant squared x over 2 dx. So you want to go back in time, which I guess that's the good thing about summer, is it wasn't too long ago. When you first learned derivatives, we had exactly two properties. We had the constant multiple rule, and we had the sum and difference rule. All right? So looking at this, we got all kinds of stuff going on in there. What do I know about derivatives or antiderivatives? They respect addition and subtraction. So I can break this integrand up over the addition and subtraction. I can write this as the integral of 3x dx minus the integral of cosine 2x dx plus the integral cosecant squared x over 2 dx. All right. The first thing we apply is a sum and difference rule, just like we would do that with derivatives. You follow? Let's take a look at this 3x. That 3 is what kind of a thing? It's a constant multiple. What can I do with constant multiples? Bring them out front. So I can write this as 3 integral x dx minus, now the integral of cosine of 2x, that's one of our basic formulas. So I go back, and once again, make flashcards. Honestly, the best way to memorize these is to just work through them. Here we're integrating cosine of kx dx. It's going to be more or less sine of kx, but to cancel out the constant, I have to divide by 1 over k. So this would be what? 1/2 sine of 2x plus, and now remember, when you see an x divided by 2, let's rewrite that, because that's really what times x? A half. Okay. Now, how do we integrate x dx? Well, remember, that's x to the what power here? It's not written, but it's x to the first power. So I can hit this with the power rule. With integration, with anti-differentiation, the power gets promoted. So x to the first is going to get promoted to x what? Squared. And instead of multiplying by that new power, I'm going to do what? Divide by that new power. Minus 1/2 sine of 2x. And now I've got cosecant squared of a constant times x. And I go back to my properties. Cosecant squared, it comes from more or less a cotangent. But because the derivative of cotangent is negative, I'm going to need that negative there. And it's not quite the cotangent of a half x, because if I took the derivative of that, I'd have a factor of a half that comes out. So to counteract that, I need to divide by that 1/2. And when you divide by a half, you're really multiplying by what? 2 plus c. So I guess our final answer, we could write this as 3 half x squared minus 1/2 sine of 2x minus 2 cotangent x over 2 plus c. And once again, the best way to check your answer is to take your answer and take the what? Derivative, and show that you can work it back into what the integrand is. You follow? All right, let's take a look at number 2. We're looking at the integral here of the square root of x minus 3x cubed, all divided by 4x squared. Now, once again, you got to think back to the first day you worked on derivatives. You had only 2 rules. You had your 2 properties. You had your sum and difference and your constant multiple rule. And then as far as formulas, you just had your power rule and your basic trig rules. All right. So what kind of strategy would you employ here to get things going? It was one of the strategies we had in early days of derivatives. What can we do with the numerator? Break it up. Let's take a look at what's going on here. How are we going to rewrite that square root? How do we always rewrite the square root in calculus? The 1/2 power. Let's take a look at what's going on here on that first term. I've got a 4 in the denominator. That means I've got a constant multiple of what here? 1/4. Now what do I do here? I've got x to the half divided by x squared. So how does this happen? If I have x to the m power divided by x to the n power, what do I do with those exponents? You subtract them, m minus n. So I'd have 1/2 minus 2, so minus 3/2. And what's the coefficient here? I've got a factor of 3 in the numerator, factor of 4 in the denominator. And what's going to be my power on x here when it's all said and done? X to the first. So x. All right. So once again, do a little bit of algebra. Break up the numerator. Simplify using exponent properties. Now I can use what property here? Sum and difference. What can I do with the 1/4 and the 3/4? Factor them out. Constant multiple rule. And now I can hit it with the power rule. All right, here we go. We got x to the minus 3 has power. When you integrate, it's the derivative backwards. So instead of subtracting 1, I'm going to be doing what? Adding 1. When you add 1 to negative 3 halves, what do you get? Negative 1/2. And instead of multiplying by negative 1/2, I have to divide by negative 1/2. So when you divide by negative 1/2, that's the same as multiplying by what? Negative 2. So this would be negative 2 x to the minus 1/2 minus 3/4. Once again, when you see x on its own there, that's really x to what power? The first. So once again, power rule. For antiderivatives, you go backwards. So instead of losing a power, you gain a power. So x to the first is going to become x squared. And instead of multiplying or dividing by the power, we're going to divide. And to capture all the antiderivatives, I tack on a what? C. So we can simplify this. Okay. Now, since you had to do some algebraic maneuvering in the integrand before you took the antiderivative, when you check your answer taking the derivative, you're going to have to reverse all that algebra, which is good practice on algebra. So you would take the derivative, you'd get back to this part when you took the derivative, if everything's going according to plan, but then you'd have to redo the algebra that we did here. So we'd have to rewrite the powers, get a little common denominator to get back to the original. Okay? All right. Oops. All right. Any questions on this example? Do you see how it's the same basic strategies we did for derivatives? Like if you go back and look at section 3.3, it's the same strategies we used in section 3.3. Let's take a look at number 3. Integrate secant of x times secant of x minus tangent of x dx. So just like we didn't have a formula for division and we had to simplify with algebra first, we don't yet have a formula for multiplication. That's usually what you start Calc 2 off with, is a multiplication rule for integrals. That being said, you wouldn't use it here because what's one of the strategies we had back in section 3.3? What can I do with this? I can do the multiplication ahead of time and then I can break it up. You follow? So what's secant times secant? Secant squared. What's secant times tangent? Secant times tangent. So I don't have a rule for multiplication, so I'll just multiply it out, but now I do have a rule for subtraction. So the integral of secant squared minus secant tangent, thanks to the difference rule, is the secant integral of secant squared minus the integral of secant tangent. And what's the integral of secant? I need a function whose derivative is secant squared. The answer is tangent minus, I need a function whose derivative is secant times tangent. The answer is secant. how do I capture all the antiderivatives? I slap on a what? Slap on a C. Make sense or not, folks? All right, now, example 5 is a video. So once again, that would be a recommendation. You know, when you're off looking at calculus again today, the first thing I would do is review what we did together and then try example 5. I've got the answers there for you. All right, and there's a video of me working through all of these if you get stuck. Okay. All right, let's look at an application. So these are classic applications. So I know some of you will be taking like a calculus-based physics class. This is the kind of thing you're going to see in a calculus-based physics class. Whoops, did someone just pop in? Oh, welcome in, Elsa. But let's kind of review here our one-dimensional motion here on physics. So we have S of t. This is the position function. This tells you where you are at time t. If I take the derivative of the position function, I get the what function? I get the velocity function. So this is how fast, which is the absolute value of velocity, that's your speed, and what direction, that's the plus or minus you're heading. And if you take the second derivative of position, which is the first derivative of velocity, that gives you the what? Gives you the acceleration. That's your rate of change of velocity, and this is under most, well, not most, I shouldn't say that, under suitable conditions, that's directly proportional to the force acting on the object. This is the rate of change of velocity. So what is a common thing to do is, suppose we know the acceleration of the object. Right? Moving along the line x equals 2 is given by a of t equals sine of 2t. So the schematic here is we've got this vertical line x equals 2, and we've got this object moving up and down this line. Okay, so just moving up and down. And the acceleration, whoops, is a of t equals sine of 2t. So remember, the sine wave, it oscillates up and down. You follow? So the acceleration of this object is sinusoidal. So what do they ask us about? What are we asked to find here? If the initial velocity of the object is -2, find a formula for the velocity of the object. Okay. So they want to know if the initial velocity is -2, find a formula for the velocity. So, coming into today, I knew that the derivative of velocity is acceleration. So the derivative of the velocity is the acceleration. In the language of antiderivatives, in the language of integrals, that means that what? The velocity is the what of the acceleration? Antiderivative. Okay, and notice the independent variable here is given to us as t, ostensibly for time. So notice that that's going to be the variable of the integration. Does that make sense? Oops, all right, so v of t equals the integral of sine of 2t dt. And this is one of those basic formulas. So I head off here. Once again, you know, make flashcards. go off to Quizlet or whatever. When you integrate sine of a constant times t, it's going to be more or less minus cosine of that constant times t, but I have to divide out that constant. So this is going to be what then? Negative 1/2. We got to tack on a what? C. Okay? Now it asks us for the velocity function. This is actually a whole family of velocity functions. You follow? So they've given us a piece of information. They told us the initial velocity was what? -2. Now when they mean initial, when you see the word initial in these types of things, initial means what? That's when t equals 0. So this is actually telling us that when you plug 0 into the velocity, we should get out -2. So this is called, in the business, this is called an initial condition. An initial condition is a point that helps us pin down which of these functions we want. So of all the velocity functions we want the velocity function that goes through the point 0, -2. We want the one where you plug in 0, you get out -2. So we just do this. We plug 0 in. So we got -1/2 cosine of 0 plus c equals -2. What's the cosine of 0? 1. So what do we get for our c? Okay. So our velocity function is now -1/2 cosine of 2t minus 3/2. And the way you would check your answer is you could take the derivative to show that you get sine of 2t for the acceleration. You can plug 0 into this to show that you get -2 for the velocity. Make sense or not? Nope, so let me get back to it here. Okay. If the initial position is the point 2, 5, find a formula for the position of the object. Okay, so once again, we go from what we learned back in chapter 3. The velocity is the derivative of the position, and we spin this around. That means that the position is the what of the velocity? Antiderivative. Make sense or not, folks? So now I'm going to put that in. The velocity was -1/2 cosine of 2t minus 3/2. And once again, the variable of integration here is dt. So now I work through using properties of antiderivatives. What would be the first property I could use here? Sum and difference rule. So it would be integral -1/2 cosine 2t dt minus the integral 3/2 dt. What can I do with these constants? Whoops. Move them out. -1/2 integral cosine 2t dt minus 3/2 integral. And then what's left inside? If I factor out the 3/2, what's left? 1 dt, or just dt. And now I run off to one of my basic formulas. Integrating cosine of 2t, more or less, cosine of 2t comes from what? A sine of 2t, but the derivative of sine of 2t would spit out a factor of 2, which I need to compensate by putting in a factor of what? 1/2 minus, now be careful here, It's minus 3 halves what? What's the integral of 1 dt? What function has a derivative of 1? Just t, correct, good. Common mistake is to put an x in there, but I'm not integrating with respect to x, I'm integrating functions of what? T, okay? So here's here's a family of position functions. Once again, I've picked up that constant c. I got to figure out what that c is. So, did they give us an initial position? Sort of. They said the initial position of the object is the point 2, 5. Now this is, I did it like this because this is how the book does it. When they give us the point 2, 5, that's an xy pair. You follow? We're looking at functions of t, so some people think that, and it's easy to make this mistake, they think that the t is 2, but they're looking at on the xy. We know that we're on the line x equals 2. You follow? So the position they're talking about here is that y value 5. Does that make sense or not? It's like on that word problem on Monday. The way it was phrased tripped me up. Hopefully you got that correction on email there. But as soon as people walked out, Emily was here, it occurred to me what they were trying to do with that problem. But anyway, it's the same kind of thing here. So initially, the word initial still means t equals 0. The x is always 2 because you're on the line x equals 2. So this is the position that they're tracking. Does that make sense? So once again, it's just I'm trying to head off some challenges in the homework. All right, so s of 0 is 5. So I go back, I plug 0 into my function, minus 1/4 sine of 0 minus 3 halves times 0 plus c is 5. In this particular case, what's the sine of 0? So everything zeroes out, and I actually get my constant itself is 5. And so my final answer here, minus 1/4 sine of 2t minus 3 halves t plus 5. Now once again, if you're going to check these on Desmos by taking derivatives, you want to make sure you use your variable as x. Okay. You doing a lab today?
Yeah.
What lab you doing? You know, that was his specialty. Uh-huh. And he always runs out of time to really give it justice. But yeah, he was doing stuff with anti-corrosion stuff out in Wyoming. Yeah, so using electrochemistry to do stuff like that.
I think he mentioned it in one of his lectures actually.
There's some nice math behind that Nernst equation too. Enjoy. Okay. Now there's one like this. I forget if it's on your test or take home. Okay. Now, here's a video. This is a really good one, especially for you, Emily, since you're going, or both Emily, since you're going into, going to be taking physics. What's nice about antiderivatives in calculus is we can derive one-dimensional motion, assuming the only thing acting on the object is gravity. We can actually derive this formula, which no doubt you've seen in pre-calculus and algebra classes. You know, the height of a basketball off the ground is given by this if you ignore wind resistance. So we can derive from first principles, force equals mass times acceleration. We can derive from first principles, okay, if the acceleration is gravity, and gravity is acting downward for us, with initial speed and initial height, we can get the formula for that motion, which is pretty cool. Then you got various and sundry homework in here. Now the way it's listed is it's listed every other odd, which gives you 20 or so. But if you want more practice, I would recommend going and doing what? Every odd. Okay. And once again, I highly recommend checking your answer by taking the derivative.